All right, so standard deviation and or variance is going to be a little bit tougher because there's no test on your calculator that you can use that I know of. If there is and you find it, please let me know because it'll save us time. So we are going to have to evaluate its test statistic by hand. And so there's a lot of formulas there, or a lot of letters there. The X looking thing is chi-squared, which going back to when we did variance and standard deviation before, the null chi-squared is equal to n minus 1, so sample size, we know sample size. S squared is the sample variance, or if they give you a sample standard deviation, you can just square it. And then sigma squared null is the variance in the null hypothesis, or if the null hypothesis has a standard deviation in it, then you can square that. So this test statistic, instead of having a p-value and an alpha to compare, we're going to be comparing test statistic to critical value. And so we're going to practice finding the critical value using the chi-squared chart. So on the Google Classroom, I believe that I've moved this to the top. If not, it was originally from March 30th, or let me know and I can repost it. But I'm going to use this chi-squared distribution chart. And so they say determine the critical value for a right-tailed test of a population standard deviation with 18 degrees of freedom at the alpha equals 0.05 level of significance. So the first thing that I'm noticing is that it's right-tailed. And if you look at this chart, it talks about area to the right, which means when they say alpha, this is the alpha that I'm going to use. So I'm just using the chart, 18 degrees of freedom, alpha is 0.5, so 18 alpha 0.5 looks to me like 28.869. So the answer to the critical value is 28.869. So after I evaluate a test statistic and I compare them, I would be able to either decide to reject or not reject. Part B says determine the critical value for a left-tailed test. For a sample size of n equals 23 at the alpha equals 0.01 level of significance. So because the chart is the area to the right, the alpha of 0.01 on a left-tailed test corresponds to 0.99 on the chart. So I'm going to use an alpha of 0.99 on the chart. Also, please be aware of the fact that they gave me n. And if you remember or not, the degrees of freedom is n minus 1. So I'm actually going to be using 22 on my chart and 0.99. So when I match those two up, I get 9.542. So the critical value is 9.542. So a couple of extra things to be aware of. Part C, determine the critical values for a two-tailed test of a population standard deviation for a sample size of n equals 30 at the alpha equals 0.05 level of significance. So first of all, the degrees of freedom, I'm going to be using 29. And then second of all, they say critical values. There's going to be two of them, and I'm going to think of splitting the 0.05 on either end. So that's 2.5 on each side. So I'm going to find, well, it's chi-squared, so it's not normal, but I'm going to look for the 0.025 mark, and then I'm going to look for the 0.975 mark, because that's 2.5% on each side. So for 29 degrees of freedom, which is right here, I'm going to be looking at 0.975, so 16.047, and then the 0.025, which is 45.722. So the two critical values are whatever I just said, 16.047 and I forget, 45.722. And so determining whether to reject or not depends on if it's a left-tailed, a right-tailed, or a two-tailed. So let me grab, you can't see the paper that I have here, but it's what I've got. So I put the shaded is the rejection zone. So on the two, this is not drawn to scale by any means, but it would be the two outside portions. And then for a left-tailed test, you would reject it if it was to the left, and then, or too far to the left, and then for a right-tailed test, you would reject it if it's too far to the right. So I don't know the numbers in the scaling. It'll be different depending on the problem, but if I had a two-tailed test and my critical values were 16.047, so if this was 16.047 and this was 45.722, and I got a test statistic of 18, I would not reject. If I got a test statistic of 48 or of 12, I would reject. And so for the left-tailed test, where it's this one, 9.542, if I got a test statistic of 3, I would reject. If I got a test statistic that was greater, I would not reject. And then for the right-tailed test of 28.869, it's actually a little bit different because now I would reject if it was bigger and I would not reject if it was smaller. And that goes back to the fact that I am not comparing a p-value to an alpha, I'm comparing a test statistic to a critical value, which is just different than what we've done before.